Thank you. OK, so as I was saying, I'm really excited to be here because not only do I reside here, but I was a web developer before I came to AI. And there's nothing I get more excited about than helping other web developers make that transition to AI as well. And as web developers, we had something really, really unique. And that is the humble view source that's inside every web browser. Who among us hasn't actually learned something about web development, maybe even got started with web development thanks to going to view source and learning something about it? And we talk a lot about the importance of open source in the ecosystem, and it's really important. But I would argue that view source is also really important. Open source is, yes, it's code that's available, but it's still code for specialists. You have to download it, you have to compile it, clone the repo, maybe work out some dependencies. View source is different. View source comes to you. It steps out from the podium, goes into the audience, and actually is running on your machine locally so you can inspect it, you can debug it, and you can tweak it and learn from it instantly without having to do any of that dependency management. It rewards curiosity. And so as web developers trying to learn AI, it would be really great if we had something like view source for AI, where we could take a large language model, not to run for production, but to run to learn, that runs in the browser, in a language I know, like Vanilla JavaScript, and that I can debug locally on my machine. Wouldn't that be great? Well, today is your lucky day, because that's what I've built. If you go to Spreadsheets are all you need, .ai/GPT-2, I apologize for the long name, you will find a view source implementation of GPT-2, OpenAI's penultimate open source model. This runs entirely in the browser. It's interactive, it's debuggable, and it's not written in some esoteric framework. It's written in vanilla JavaScript. The matrices are just plain JavaScript arrays. Let me show it to you for a second. So here we go. That was the wrong way to go. There we go. So here's the web page. And the first thing you'd want to do when you want to run it is go here. There's a link you'll click. You download a giant zip file, and then you drag the contents of that zip file into this part of the web page. From that point onward, the model is running entirely locally in your browser. That means you can enter a prompt, like a prompt right here, and you can hit the run button, and you can disconnect your internet connection, and it will predict the next word, just like your standard large language model. If you want, you can go through these code blocks one by one, clicking them to see how a real large language model works. Even better, you can go into the model, and you can debug it using Chrome DevTools. So let me do that. So I'm going to go here. I'm just going to take this part here, and I'm going to type in debugger, semicolon, and then I'm going to ask to run it. I don't know if you can see it way in the back, but up here in the right, I am stepping through a large language model that once was considered too dangerous to release entirely in my browser. Now, why do we study GPT-2? Seems a little old, right? We're at GPT-5 now. Well, GPT-2 is the granddaddy of all the models you probably know, whether it's ChatGPT, Claude, Gemini, or Llama. They all inherit from GPT-2. It's their granddaddy. If you understand GPT-2, you understand 80% of the first principles that go into a large language model. The other key thing is that GPT-2 is fairly small. Believe it or not, it's only about 600 lines of code. Right? This model that was considered too dangerous to release. Yes, it's big in terms of number of weights of model parameters, but the actual code to run it is only about 600 lines. I know you have read, let alone written, probably more than 600 lines of code. So this is a lot easier than you might think. So even though it's only 600 lines of code, there's going to be a lot of new concepts. So what I'm going to do for the rest of this talk is give you a crash course in those concepts to give you a jump start. So let's begin with what you're probably already familiar with. A large language model is really a giant autocomplete engine, right? You're given passages like this one, Mike is quick, he moves, and we ask it to fill in the blank. Now, as a human, you know a reasonable answer might be the word fast, or maybe the word quickly, but how do we get a computer to do that? Well, here's a fill in the blank that a computer can solve very easily. 2 + 2 = 4. It's easy for a computer because it's math, right? Computers are very good at math, even if we make the equations and calculations really complex. So what a large language model has figured out how to do, or what we've figured out how to do with the large language model, is take what is nominally a word problem, filling in the blank, and turn it into a math problem. In order to do that, we start with 2 steps. We first have to tokenize the input and then convert it to a numerical representation. Let me walk you through those 2 steps in a high level. So the first step is tokenization, where we take the input text and we break it out into pieces. Now, you might think we break it into characters or we break it into words. It turns out we break it into these things called tokens. Now, very common words will be their own token. In fact, in the example I use, every single word maps to a single token, but it's not uncommon for a word to go to 2, 3, or more different tokens. Now, you might wonder, why do we bother with this tokenization business? As a developer, why don't we just do something like ASCII, right? Just look at it on a character-based basis. And there are models that have worked that way. The issue with doing that, to simplify, is that what you end up with is very long sequences. Take the example sentence from the previous slide. Mike is quick, he moves. That's only 6 tokens. If we looked at it on a character basis, it would be 24. So your context length gets a lot less usable if it's taken up by raw characters. It's a lot more work for the model to deal with. At the other end of the spectrum, you're like, okay, why don't we just make each word its own token? And you will get a shorter sequence. But the challenge is that your vocabulary is going to balloon because you need every single word in the dictionary. Oh, wait, I'm looking at text on the internet. I need all the foreign languages. I need typos. I need misspellings. It's not workable. So subword tokenization is effectively a compression step that balances the size of our possible vocabulary with a reasonable sized length of a sequence. And what we basically do is we take the most common words and we give them their own token. And then if it's an uncommon word, we learn how to build it out of Lego blocks of smaller subword units. That's the tokenization step. And if you're in the application, you'll see it here in this step called final_tokens. There'll be 2 rows. The first one is how your prompt got broken into tokens. And the second one is going to be what are called the token IDs. They're just its location in the dictionary. OK, the next step is what's called an embedding. And you actually heard about embeddings in the previous talk as well. And that's taking these tokens or these words and turning them into a mathematical representation. Now, previous slide simplified this by showing each word going to a single number. What happens in practice is it goes to a long list of numbers that we call an embedding. In the case of GPT-2, that embedding is 760 numbers long. So every single token gets the same number of numbers to represent it. Even the lowly period gets 768 dimensions or numbers to represent it. Now, this word embedding can feel intimidating or foreign, but what I want you to think about it as is as a map for words. What we're trying to do is put the words on a map where they're grouped by similarity, right? You're used to a regular 2-dimensional map where you take a point of interest and it's got a latitude and a longitude. All we're doing is the same thing, except instead of just 2 dimensions, we're building a map that has many, many dimensions, 768. And the goal of our map is to put words that have the same meaning close to each other. So here, for example, we've got happy and glad. They're both emotions. They're sitting all the way here on the left side of our word island, versus dog and cat, unrelated. They're animals. They sit on the right side. And then sad, well, that's an emotion, so it goes on the right. It's close to happy and glad, but you can't use it interchangeably with happy and glad like you can with those two. So it's maybe slightly further down in its own kind of word province on this map. The key thing is if we do this clustering well, putting similar words in similar spaces, what we get out are vector relationships that capture semantic meaning. So as an example, I want you to imagine we've clustered countries like Japan, Italy, and France together properly, and our algorithm also clustered their capitals together, Paris, Tokyo, and Rome. Well then, what we've got is a very consistent vector relationship from the semantic position or the embedding position of a country to its capital. And in fact, if somebody gave me another country, I know I just take that same direction and I end up with the capital to that country. A powerful practical demonstration of this is actually Golden Gate Claude, which came out last year. This was a version of the Claude large language model that only talked about the Golden Gate Bridge. You asked it for a math problem, it gave you an example involving the Golden Gate Bridge. You asked it who it was. It wouldn't say, I'm Claude, the AI model. It would say, I'm the Golden Gate Bridge. And the way they did this, to simplify, is they found a Golden Gate Bridge vector in the latent space, in the embedding space. And they basically took every embedding that came in, and they just shifted every single one. You type the word dog in, it would be the dog with the Golden Gate Bridge. It just got shifted. And then lo and behold, the model starts saying Golden Gate Bridge every other word. So one thing you might be wondering is, well, where the heck do these embedding values come from? And the unsatisfying answer is, well, they're learned by the model through a bunch of algorithms. But we can get a kind of intuition about what the model's doing. And that's learning from word statistics. So imagine you're a model being trained on text from a variety of sources. And think about words like ice, steam, hot, and cold. And what you would notice, if you were like an alien or the LLM model, is that ice and cold tend to co-occur together, and steam and hot tend to co-occur together. And so, if you're an alien, like, I don't know what this cold, ice, steam, hot things are, but I know whatever cold is, ice has got it, and steam does not. And whatever this hot thing is, steam has got it, and ice does not. I can just tell that from how often they co-occur. And it turns out, and this is something we do in the AI class I teach online, is we build our own embeddings just by taking pages from Wikipedia and just counting how often words co-occur with each other, and you can actually build a primitive form of embeddings. So mentally, I want you to think of these as capturing really just the co-occurrence statistics of how words interact with each other. Okay, enough about where embeddings come from. How do we actually use them in the model when we're making a prediction? Well, when a provider or model producer like OpenAI releases a model into open weights, they give us a large list of parameters, usually billions or millions of them. Some of those include the mapping of embeddings, usually a table like this one, model_WTE, it's called in GPT-2, which is a two-dimensional matrix where the rows are just assigned to every single token, and the columns are simply the embedding values for that particular token. So if I want the embedding for cat, I just go to the right row, and I just pull it out, and I append it to my growing context length. If I want the next word is man, I'll go to that row, I'll pull that embedding out, and I'll append that onto my growing context length. And that's how we take basically your input and turn it into embeddings. In fact, here's the code for doing that in the application, tokens to token embeddings, and it's like 16 lines. It's just going into an array saying, what's your ID? Oh, you're at this position. Pull that out, and then I append it to my growing matrix. And voila, we've turned our text into a numerical representation that's really a large list of numbers, a two-dimensional matrix of them. So now that we've taken our input text and we've turned it into a math representation, now we actually have to do the math calculations. And the two key steps for this are words you've probably heard of, but maybe not familiar with how they operate, called attention and the perceptron. And I'll dive into each of those in a little bit. So let's talk about attention. In the attention step, these words, or rather the embeddings of these words, get to talk to each other to see if they interrelate and should share context. So conceptually, you can think of like he is a pronoun. It might go look at Mike, right? That's the antecedent. Maybe there's some information there. Or moves and quick might interact, right? Because quick in English has multiple meanings. It can be a body part, like the quick of your fingernail, or it can be moving around in physical space. But knowing we're talking about moves later on is useful context for the model to disambiguate that. But what does it mean for them to talk to each other? Let me go into that in just a little bit more detail. So think about this word moves, right? We've said we've given it a mathematical position in this map for words in space, right? Sitting out here. But moves, gets used in a lot of contexts. Sometimes we're talking about things that move fast, like rabbits and cheetahs. And sometimes we talk about things that move slow, like penguins, or here in the Pacific Northwest, slugs. I see them in my backyard all the time, outside of the summer. And so you can imagine there's a point in this space near to moves that represents moves in the context of rabbits, and there's another point in space, moves in the context of slow. If you will think about this lower left one is moves when people are talking about slugs, and the upper right one is moves when it co-occurs with fast things like rabbits. And so what happens is when these tokens are talking to each other, what's happening is their embedding values are kind of getting transformed and intermixed into each other. So quick kind of gets intermixed into moves, and you can think of it conceptually as having the net effect of shifting the position of moves in our map from regular generic moves to, oh, this is the moves only in the context of fast. So that's how we've incorporated the context of the other words into the word we're looking at in its embedding. One area that's probably the most salient place to look at this action is inside block step 7. This is where you see a table that takes every one of our input tokens, Mike is quick, he moves, against every other one of the input tokens, Mike is quick, he moves, and you can see how much attention each token is paying to the other token. And each of these rows must add up to 1. So what you read these are as percentages. So if you look at column 1, row 5, you see 0.48. That means basically 40% of he is looking at Mike and is going to incorporate that into its context. OK, that's attention. So now we've got all these tokens that have some sense, not just of what they mean normally when we refer to them, but what they mean in the context of the sentence that they sit. So that gets us to the next step, which is the perceptron. This is where we're actually going to make the prediction of what the next word is. Now, the thing to know about the perceptron is it's really a great imitator. We train it with known inputs and outputs, and afterwards, if we give those inputs again, it will give us the output we trained it on. So during training, the MLP, or multi-layer perceptron, was given a list of known good inputs and outputs. Basically, there was maybe something like this on the internet. Mike is quick, he moves quickly. So no, quickly was already there. And they pulled that last word off, and then they asked the model, hey, anytime you see these words, especially moves in the context of quick, right? It's fast move. I want you to output the embedding value of quickly. And they give it example after example after example of that. And they used an algorithm called backpropagation, which slowly tuned the model such that anytime it sees moves in the context of fast words, it will output the embedding value of quickly. So now it's learned how to make that prediction. Now it's not just moves all the time, it's only moves in this context of fast. If it was maybe moves in the context of slow, it would know to say slowly. That would have been another set of sentences. So what's great about this is we're not explicitly training it. We're just grabbing text as it naturally is on the internet, chopping off the last word, and then sending it into the model and saying, no, here's what some human wrote a long time ago that should have been the right answer. And it learns to imitate the text it's been given. You can see this in steps 13 to 15. I don't have time to go into all the math of it, but that's basically the core heart of the operation. OK, now we have taken our input text. We've tokenized it. We've turned it into a mathematical representation that's an embedding. We've let the tokens talk to each other to share context with attention. And then we asked the MLP, the perceptron, to make a prediction based on all that context. And it gave us an embedding. It gave us 768 numbers. Where in this diagram, I've simplified it down to just one. But we've got a problem. This number that comes up with is probably not a number in our dictionary of known tokens to embeddings. Right? So here, for example, we've got 231. There's no dictionary number for that. So what we do is we say, well, what are the tokens we do know about? Which ones are the closest? It's probably one of those. So in this example here, we're like, well, quickly is 232, so maybe that's a good answer. But fast is 240. Maybe that's a good answer too. So what we do is we basically create a probability. And we say the words that are closer will get a higher probability. And the words that are farther away in their embedding space on our map for words, they're very unlikely. Basically, this whole process took all the words, and it gave us a point in our embedding space and said, this is what I think the prediction is. And then we just look around it and say, OK, what are the tokens near to it? And that's going to be the word that we predict. So let me explain that in a little more detail. So we take the output of the perceptron. That's an embedding value, 768. That's supposed to be what the next word is going to be. And all we're going to do is we're going to multiply it by that table I told you about earlier, model underscore WT. What was this? It was the list of all our known tokens. And we're going to multiply them. What does this action do? It's basically taking our prediction and multiplying to all the known tokens. And what that does is it creates a dot product. And things that are similar will have a higher value dot product than things that are different, right? Things that are orthogonal will have a dot product of 0. If they're very similar, they'll be closer to 1. And so what you end up having is what I like to call token scores. Officially, they're called logits. But you can think of these as the higher the value is, the more similar that token is to our prediction. And so you could take just the highest value and say, that's the prediction. In fact, that's what happens at temperature 0. We just take the thing with the highest logit value and say that's your prediction. Now, if you want to use a probability distribution, which is what most models you use do, and you have this temperature parameter, then we need to take this set of scores and turn it into something that adds up to 100%. That's a mathematical operation called normalization. For that, it's often used this thing called Softmax, and the temperature parameter is really just changing the distribution of that normalization. And that will give you a probability distribution. If you want to see the predicted token, you'll see it at the very end of the application, at the bottom of the web page, at predicted_token. It'll also tell you what the maximum logit value is, the token ID, and what the actual word is. And again, if you put this into any implementation of GPT-2, say on Hugging Face or elsewhere, and you set it to temperature 0, you should get the exact same output This is the full open weight compatible version of what was released by OpenAI for GPT-2 small. Okay, so I've thrown a lot at you. To sum up, what we did in this whole process was we took text, we turned those texts into tokens. You can think of this as just pieces of subwords, Lego blocks for words. Then we took those Lego blocks and we gave them a point in space that's supposed to capture their meaning, right? That's the map for words. And then we did a bunch of number crunching in this map, moving things around to capture what their true meaning was given the context of the rest of the sentence. And then we gave it to the Perceptron to make a prediction. Give us a point in space where you think the right next word is. And then we turn that back into text, either by doing temperature 0, taking the most closest thing, or making it a probability distribution where we roll the die and give back a predicted token. And then we get our next token. So I know I've thrown a lot at you. This was a crash course in machine learning, like AI fundamentals. What I often tell my students, and normally this is an 8-hour, 2-week class, is don't expect full mastery immediately when you see this. What you should expect, though, is the feeling that full mastery is within your grasp. So don't expect it immediately, but I hope you get the feeling that this is something you could learn. You could go through 600 lines of code and learn. And these magical LLMs don't have to feel like magic and mystery anymore. Hopefully they can feel more like machines. Thanks to these view source principles. Which brings me to one more thing. I opened by talking about how important I thought it was to bring what I call view source principles, stuff that's browser-based, really embraces the reach, distribution, and the platform of the web, and the accessibility, and bringing the code to you to make it easy to use and inspect and learn from as easy as possible. And I think that's really important for learning AI. But I also think it's important for building with AI. So I'm really excited to share with you Spreadsheets Are All You Need notebooks. These follow the same principles of vanilla JavaScript, debuggable, interactive, and browser-based, but for creating AI workflows. Let me give you a quick demo. We'll have to, there we go. Okay, so this is an example. Now this is running entirely, well, the model in this case is now running in the cloud. You bring an AI key for an API key for whatever your model is. And then instead of just having code blocks, which you saw in the original application that you got to run individually or all at a group, we now have the ability to have code steps that are vibe coded. You can describe the code you want and it will generate that code, or you can write it yourself in JavaScript. You can have table steps, these are data, and you can have prompt steps, these are prompts for the model, and then you can have input steps, these are user input. And you can chain these together into a workflow that you can share with anybody. So here, for example, is a workflow for creating a blog post. And it works through asking the user what the topic is, and then working through a couple of ideas, refining those ideas into the one that fits best for their audience, and then finally turning it into an outline, and then finally a post. Now, you can debug this, again, through Chrome Debugger or your browser dev tools, just like you can the original GPT-2 implementation, but also has an additional special power. If I hit this export button, let me get out of full screen, and I click here. I don't know if you, maybe I'll make it even more clear. Let me go here, and I take that file that got exported. So I modified it. I just double-clicked on that. There was no server, nothing to run, nothing to install, no dependencies. This is a runnable HTML file that captures a prompt template, a prompt workflow, that I can take and I can put it on Dropbox, I can email it to somebody, I can share it with anybody I want, and they can instantly click on it and run it. They don't need any special software. They don't need to manage dependencies. It is usable by almost anybody who has a browser on their platform. So it's a great way to share prompt workflows and templates. So if you are learning how AI works, I encourage you to check out Spreadsheets Are All You Need GPT-2. I also have a class I teach on it that's also available, but the web application is free for anyone to go to the web and just try out. Also available for AI consulting if you're interested in that. And then if you're building a workflow around AI or you want to create a workflow you want to share with others, I encourage you to check out Spreadsheets Are All You Need notebooks. It's on GitHub. It's an open source project. Check it out. jump into the Discord and give me feedback. Hopefully, these are useful to you, and best of luck on your AI journey. Thank you.